In this module, we are going to discuss one of the key components of superscalar process, that is dynamic execution core. So, we know that in a superscalar processor, we have the in-order fetch, in-order decode, in-order dispatch, but we have out-of-order execution, and finally, in-order the commit and the in-order retirement will be there. This dynamic execution core is the one which actually implements the out-of-order execution of the instructions. And this dynamic execution core actually resembles a refinement of Thomas-Solow implementation. So, we know that the execute stage is sandwiched between the dispatch stage and the complete stage in our superscalar pipeline design. So, in the dispatch stage, we have the decoded instructions, and these decoded instructions will be dispatched to various reservation stations. And at the time of dispatch, the operands may be ready. So, we take the operands if they are ready and dispatch these operands along with the instruction to the reservation station. And if the operands are not ready, then we will dispatch the register tags along with the instruction to the reservation stations. So, when the operands are ready, we can read the operands either from the architectural register file or from the rename register file, and that will be fed here to the reservation stations. And again, among the several reservation stations, we are going to select a suitable reservation station based on the type of the instruction. And each of these reservation station is going to take care of issuing the instructions that are stored in the reservation station to the corresponding functional units. And here we have multiple functional units, and different functional units may take different latencies. So, as a result, the instructions can finish their execution in different number of cycles. And again, an instruction can be issued to a functional unit only when both of its operands are ready as well as the functional unit is free. If any of these things are not ready or available, then we cannot issue that instruction to the functional unit. So, as and when the instruction is finished its execution, then we can forward the computed value along with the registered tag through this bus back to the reservation stations as well as to the rename register file. This is mainly to ensure that all the dependent instructions will get the operands as soon as the parent instruction finishes its execution. And as and when the instruction is finished its execution, then the value will be updated in the reorder buffer also. So, we have this completion buffer, also called as a reorder buffer, and from there we will complete the instructions in the in order. So, in order to provide the in order commit in this stage, we are always going to select the instructions which are at the head of the reorder buffer. We take that instruction and then send it to the completion stage for the completion of the execution of that instruction. So, when I say an instruction is going through the complete stage, so the values will be written to the architectural registers specified in the instruction. And also, whenever the instruction is going through the complete stage, if the value is there in the rename register file, then we will write that value back to the architectural register file by using this mapping mechanism between ARF and RRF that we discussed in the previous modules. So, effectively, the dynamic execution core consists of a set of tasks. One is the instruction dispatch, the second one is instruction execution, and third one is instruction completion. So, as part of this instruction dispatch, we take care of the register renaming, allocation of entries in reservation station as well as the reorder buffer, and advancing the instruction from the dispatch buffer to the reservation station as part of the instruction execution. We issue the ready instructions to the functional units and execute these instructions on the functional units, and as and when the computation is done, we will forward the results through using this forward bus back to the reservation stations as well as to the rename register file. And once the instruction is finished its execution, and if it comes to the head of the ROB, then we will complete that instruction by writing the values to the architectural register. And we already discussed in the previous modules the role of rename registers, because in order to eliminate the name dependencies among the instructions, we are going to use register renaming. So, as a result, both the output dependency as well as the anti dependencies can be eliminated from the instructions. And we allocate an entry in the reservation station because the instructions will be waiting in the reservation station after they are dispatched, and they will wait until both the operands are available as well as the function unit is available. And we also allocate an entry in the reorder buffer for all the instructions which are having the in-flight status. So, that is nothing but all the instructions that are there either in the reservation stations or that are executed by the functional units, or those instructions which are finished their execution but not yet completed, will have an entry in the reorder buffer. And we already discussed the reorder buffer is mainly helps in committing the instructions in in order. And so, once we find a free entry in the reservation station, then we can dispatch an instruction from the dispatch buffer to the reservation station. If the reservation station is full, then we cannot dispatch any instruction to that reservation station. And once the operands are ready as well as the function unit is available, then we execute this instruction on the function unit. And depending on the type of the functional unit, different instructions will take a different amount of time, and as soon as they finish their execution, we write these values to the corresponding entries in the reorder buffer, as well as we forward these computed values to the reservation stations as well as the rename register file, so that any dependent instructions which are waiting in the reservation station for this computed value will get that value, and then they can make their operands ready. And similarly, because the rename register is waiting for this computed value to be updated, so once we forward this computed value, then it will be updated in the rename register file, as well as we update the other fields of the corresponding entry to inform that the value that is stored in the rename register is the valid value. And we take one instruction at a time from the front of the ROB and we commit. And while we are committing the instructions, we are actually writing the values from the rename register file to the corresponding architectural registers, and that completes the execution of an instruction. And if the instruction is a store instruction, then in addition to the complete stage, we also have a retire stage, and in the retire stage, we are actually writing the values to the memory. So, this is the core of the Superscalar processor. The dynamic execution core is the critical component in the Superscalar processor, which actually executes instructions in out of order fashion and commits the instructions in the in order. And because of these various functional units, as well as because of this register renaming and the reservation station, we can achieve out of order execution of instructions, so that instruction execution can be overlapped for all the independent instructions, and that will improve the overall performance of the system. So, we will see how the dynamic instruction scheduler can be designed. So, the dynamic instruction scheduler includes the instruction window and its associated instruction wake up and the select logic. We already discussed as part of reservation stations that each reservation station consists of wake up logic as well as the select logic associated with it. So, this dynamic instruction scheduler can be designed in one of the two ways. In the first design, this is called as the instruction scheduler design with data capture. So, here the functional units are here and the register file is here, and in between the register file and the functional units we have this reservation station. So, here what happens is, so whenever a functional units finishes its execution, we forward the computed value to the reservation station and also to the register file. And while we are forwarding this value from the functional unit to the reservation station, this also will be acting like a wake up logic for the entries that are stored in the reservation station. And in the case of forwarding the value from the functional unit to the register file, we are actually writing this value directly to the corresponding entry in the register file. And this register file consists of both the rename register file as well as the architectural register file. So, of course, we are updating the value only to the rename register file. So, as a result, once we consider this type of design, whenever we are dispatching an instruction to the reservation station, at the time of dispatch, we read the values from the register file if the values are available. So, these values can be read either from the architectural register file or rename register file, provided the values are available in the register file. If the values are not available in the register file at the dispatch time, then what we can do is we forward the register tag and along with the instruction, so that this dispatch instruction will be stored in the reservation station with the corresponding register tags. So, in other words, the dispatch instruction will be staying in the reservation station or waiting in the reservation station until the corresponding values are available. Once the values are available for the instruction which is waiting in the reservation station, then we can issue this instruction to the functional unit. So, in order to know when to issue the instruction that is waiting in the reservation station to the functional unit, we actually use this wake up logic. So, remember, the wake up signal is just by passing the register tag to the reservation station. Any instruction which is waiting for the operands for the corresponding register tag will get a wake up signal, and the value will be returned to the appropriate location in the reservation station, so that that instruction can be now ready for executing on the functional unit. So, that we will pick the selected instruction, or we pick the ready instruction which is selected by the selection logic, and we send it to the functional unit. If we consider this type of design, our reservation station is very wide because it has to keep the register contents in each of the entries of the reservation station, as well as the forwarding path between the functional unit to the reservation station also needs to be very wider, because we are going to forward the value on this. This is one type of design, but some of the processors are following the other type of design, that is dynamic instruction scheduler without data capture. So, here what we do is we reorder these two units. So, we have non-data capture scheduling window here, and we have a register file here and the functional units here. So, this non-data capture instruction scheduling window look at all the instructions that can be dispatched to the functional units or issued to the functional units, and whenever this logic gets a wake up signal from the functional unit, then it selects the instruction and then it is going to issue to the functional unit. But while it is issuing to the functional unit, it also goes to the register file and read the appropriate values and then send it. So, in this particular design, so our reservation station will have only the register tags, but not the contents of the registers. Whenever a functional unit executes an instruction, it forwards the data through this forwarding path to the register file, but it forwards the register tag of the computed value to the reservation station. So, this tag can be acting like a wake up logic or wake up signal for all the instructions which are waiting in the reservation station. For example, consider an instruction add R1, R2, R3, where R2, R3 are the source operands and R2 is already available and R3 is not yet computed, because R3 is going to be produced by a previous instruction and which is actually executed on this particular functional unit. So, as soon as this functional unit finishes the previous instruction, so now it forwards the R3 value through this forwarding path to the register file, but R3 tag is forwarded through this wake up path to the reservation station. So that now this instruction which is waiting in the reservation station will get a signal from the functional unit saying that R3 is now ready. So as soon as it gets a ready signal here, because already R2 is ready in the instruction, so now this instruction is now scheduled to the functional unit, and while it is being scheduled on this functional unit, we read the value of R2 and R3 from this register file, and these values will be supplied to the functional unit. So then this instruction will be executed on the functional unit. So because of this non-data capture mechanism, our reservation station will be very thin compared to very fat reservation station whatever we considered in the previous design, because here with each entry of the reservation station we need to store only the register tag, but not the contents that are stored in the register. And also the wake up logic path between the function unit to the reservation station will be very thin, because here all we require is we need to pass only the register tag as part of the wake up logic, but whereas in the previous design we have to pass both the register tag as well as the computed value. So this is going to take a wider bus, but whereas here this is going to take a very thin bus. So these are the two different mechanisms in which we can design our instruction scheduler. But the problem without data capture design is, so register file read is in the critical path, because before dispatching any instruction to the functional unit or before issuing any instruction to the functional unit, we have to read the contents from the register file. So as a result, this register file requires multi-ported design, and that is going to increase the execution time also. So again, these two designs have their trade-offs. So one design is eliminating the register file read from the critical path. So as a result it can improve the performance, but it is going to take more area because of the fat reservation station as well as the wider the forwarding path. But whereas the other design, so it is not going to take significant area because we are just storing only the register tags, but the register file read is in the critical path for issuing an instruction to the function unit. So now we are going to discuss the processing of load store instructions using our dynamic execution core. We know that the load store unit is also one of the functional unit in our dynamic execution core, and this unit is going to process all the load and store instructions that are there in our the program. And so we consider load store architecture where ALU operations will be performed only on registers, but the number of registers in a typical processor is limited. So as a result, we cannot keep all the required data in our limited number of registers. So as a result, some of the required data will be stored in the memory, and we have to go to the memory to get those data. And to go to the memory, we are going to use the load and store instructions. Load instruction is going to load the data from the memory in a specified location, and the store instruction is going to write specified data in a specified location in the memory. So in order to process this load and store instructions, we have a separate unit called as a load store unit. And this load store unit is connected to the data memory, and so that it can perform either a read operation or a write operation from or to the data memory. And if it is a store instruction, we already discussed earlier that the data will be written to the memory only when the instruction is processing through the retirement stage. Similar to the ALU instructions, the memory instructions also have dependencies among them. So a memory data dependence exists between two load and store instructions if both these instructions refer the same memory location. But how do we know whether two instructions are actually referring to the same memory location? Any load and store instruction typically consists of two components. One is providing the base address, the other one is providing the offset. we have to add this base address contents with the offset to get the effective address, and this effective address is an address location in the memory generated by the program. And when we have a system supporting virtual memory, this address is effectively the virtual address. So we need to convert this address into physical address, that is the address that is stored in the main memory, and from there using that address we go to the memory and get the data from that particular location, or we have to write the data to that particular location. So as a result, so in order to identify the data dependencies among memory instructions, the first thing what we have to do is we have to compute the effective address. Once we compute the effective address, then we will know whether two memory instructions are dependent on each other or not. So in order to enforce these data dependencies, one option what we can do is execute all the load and store instructions in the program order to enforce these memory data dependencies. We should not opt for this option 1, because it is going to degrade the performance significantly as we execute all the load and store instructions in the program order to enforce the data dependencies. So we can relax the option 1 slightly by considering this ordering only for the store operations. So once we enforce that all the stores must be completed or executed in the program order, we can preserve the sequential state of the memory to recover from any exceptions happen in our program execution. And in the case of loads, we do not have to enforce this constraint. So that effectively, in order to improve the overall performance in our Superscalar processor, we can execute load instructions in an out of order fashion to improve the overall performance, but this out of order execution of load instruction can be done as long as we maintain the true dependence among the instructions and so on. So from this we know that rather than forcing all the load and store instructions to execute in the program order to enforce memory data dependencies, we can just enforce only the store instructions to execute in the program order. So because of this relaxed constraint, now we have the option to execute load instructions in an out of order fashion. Now we will consider two examples. The first example is a piece of code consists of a store instruction writing to a memory location addressed X. There is a store instruction after some time writing some data to an address location Y in the memory, and after some time there is a load instruction in the program which is going to read data from an address location Z. So now in this case, clearly we know that this load instruction is independent of these store instructions. But if we are following the option 1, which says that we have to execute all the load and store instructions in the program order, if it is so, then we have to execute this load instruction only after we execute store X and store Y. That is actually going to degrade the performance, because we know that this load instruction is independent of the previous stores. There is no point in delaying this load instruction until the store instructions are finished their execution. So in this type of scenario, what we can do is we can go ahead with the load bypassing. So this load instruction can bypass the previous store instructions, so that this load will be executed in a speculative way in an out of order fashion, and it finishes its execution. Now consider another example. So here we have a store instruction writing to an address location X in the memory. After some time there is a store instruction writing something to address location Y in the memory, and after some time there is a load instruction loading some value from an address location X. Now this load instruction is independent of this store instruction, but this load instruction is same as or dependent on this store instruction, because both load and store are actually going to perform operation on the same memory location. So in such scenarios, this load cannot be executed before these two stores, and this load actually can get the value supplied by this store instruction. So, as a result, we can exploit the other optimization to deal with the load instruction, that is a load forwarding. This store instruction is going to supply the value to the trailing load instruction, which is also pointing to the same address location in the memory. As a result, this load instruction need not access the memory to get the value, and this load can be executed quickly. So, effectively, when we have such scenarios where sometimes the loads can be independent of the previous stores, or sometimes load can benefit from the previous stores. So, we can exploit load bypassing or load forwarding mechanisms to execute these instructions and these load instructions in out of order fashion and improve the overall performance. Effectively, the option 2 to deal with the memory operations is we will go for out of order execution of loads, so that we can improve the overall performance. But when we are going for this out of order execution of loads, we have to ensure that read after write dependencies are not violated, that is like true dependencies are not violated among the instructions. As long as we ensure true dependencies are not violated, we can execute our load instructions in an out of order and speculative way, so that the overall performance can be improved. So, now in order to support this load bypassing and load forwarding, we have to see how our load store unit needs to be designed in our dynamic execution core of the Superscalar processor. So, here previously in the dynamic execution core, we consider load store unit as a single unit, but we now separate load and store units, because the operations involved with the store instruction execution will be different from the operations involved with the execution of load instructions. So, as a result, we consider two separate units. One is the load unit, which takes care of all the load instructions, and the other one is the store unit, which takes care of all the store instructions. So, in order to support the store instruction execution and completion, we will consider a store buffer, and here the store instruction which completes the address translation will be sent to this end of the store buffer, and these entries are corresponding to the store instruction which finish their execution, and whereas these entries in the store buffer are corresponding to the instructions which completes their execution. In the case of store instructions, we consider two-stage pipeline for executing the store instruction. The first stage is corresponding to the address generation, the second stage is corresponding to the address translation. And here the first stage we are going to complete the effective address calculation by adding the contents of base register and the offset, and the second stage of this pipelining is the address translation, where we go to the TLB and get the physical address for the corresponding the address whatever is generated in the first phase. And after that we say the store instruction is finished its execution, so that we write the corresponding store instruction to the store buffer, and so that the instructions will be waiting in the store buffer as long as the cache or the memory is not available for servicing the store instructions. Whenever the data cache or the memory is available, then we will select one instruction from this store buffer in the program order, and then we will write it to the data cache or the memory. So, here the store buffer is actually working in the FIFO order, because we already discussed in the previous file that all the store instructions are executed in the program order. So, as a result, we will just always select the instructions in the store buffer in the FIFO order. And here in the case of load instructions, so our load unit consists of 3 pipeline stages. First 2 pipeline stages are same as the store unit pipeline stages, that is address generation and the address translation. And once we translate the address, now we have the effective address in the main memory. Then we can go to the memory, or if our system is supporting the data caches, then we will go to the data cache using the translated address, and then we read data from that particular location to this. So, effectively the third stage of this load unit pipeline is the memory access, where the actual access from the data cache happens. In order to exploit the load bypassing, we have to modify our store unit slightly by considering an address field for each of the entries of the store buffer. By adding this extra component which has partial address of the this store instructions, we can compare the partial address of the subsequent load instructions with this and to know whether there is a match or not. And if there is no match, then we are going to execute these load instructions in out of order fashion with respect to the previous store instructions. And now, in order to support the load forwarding, unlike the load bypassing mechanism, in the load forwarding we are going to actually forward the data that is stored in the store buffer to the trailing load instructions. So, as a result, here we need to consider the full address associated with each entry of this store buffer. So, note that in the case of load bypassing, we consider only the partial address associated with each of the store buffer. So, when we consider the partial address, sometimes the partial address may match, but the full address may not match. That is not going to create a significant penalty in our design, but that considering the partial address is going to save the area overhead associated with the store buffer design. That is the reason why in the load bypassing case we consider the partial addresses. But in order to consider the load forwarding, we have to consider the full address associated with each entry in the store buffer. So that only when all the bits of the store address is matching with the load instruction address, then only we can forward the value stored in the data field of the corresponding entry in the store buffer to the load instruction. So here, whenever a load instruction comes here, we just compare the tags, and if there is a match, then for this load instruction we don't have to go to the cache or the memory to get the data. Actually the store instruction is applying. So whenever there is a match, we forward this value directly to this load instruction. Of course, so this extra component is going to add some complexity to the overall design of the store buffer, because here in the case of load forwarding, we have to consider full length address bits for each of the entries of the store buffer, and that may be like 32 bits or 64 bits depending on what are the processor we are considering. And also whenever we have the translated address, we have to search in all the entries. So for that we have to actually use a priority encoding logic to identify the latest store. We may have multiple stores writing to the same location in the memory, but we always have to consider the latest store. So for that we have to use a priority encoding logic. And also in the original design of the store buffer we have only one read port, but now because of this added component we need to have two read ports for the store buffer, and increasing the number of ports is also going to increase the access time of the store buffer as well as the power consumption in addition to the area of overhead. So these are the extra added complexities to the store buffer to support our load forwarding mechanism. So once we have the support for the load forwarding or load bypassing by using this extra component to the store buffer, now we can execute instructions, we can execute load instructions in out of order fashion. Here in this particular design, we consider a separate load buffer to take care of all the finished load instructions. Again, here we are splitting the load instruction execution into execution finish and execution complete. And at the time of execution finish, we write the data to this buffer. Now we can consider a simple example. We have store instructions store X and load Y. So this load instruction is actually coming after store instruction, and now because this load instruction is independent of the store instruction, so we can execute this load instruction in out of order fashion. So in such scenario, what we can do is, while the store instruction is issued to the store unit, we issue the load instruction to the load unit. After the second stage of the load instruction pipeline processing, we have the translated address. And so once we have this translated address, we give this translated address to this address unit of the store buffer to see whether this instruction is matching with any of the previous store instructions. And while we are doing this, we will proceed with the third stage of the load instruction pipelining by going to the data cache or the memory to read the data from the location specified by this translated address. so that at the end of the third stage we have the data from the data cache. Now, what we are going to do is, once we have the data at the end of the third stage of the load instruction processing, we write this value to the updated rename register. We write this value to the rename register to update the rename register content. So, with that we actually finish the execution of this load instruction. But remember, this load instruction is executed in an out of order fashion with respect to the previous store instruction, and we do not know whether this load instruction is actually dependent on the previous store instructions or not. That will know only by comparing this address with the addresses of the corresponding store buffer entries. If there is a match with any of the data that is stored in the store buffer, that indicates that this load instruction is dependent on the previous stores, and we have to flush this particular entry. So, if there is a match happens, then flush the alias load and all the trailing instructions, so that we can revert it back to a state where we start executing again from where we can start executing the load instruction by taking the value from the store instruction. And if there is no match happens between this translated address of the load instruction with any of the translated address of the previously finished store instructions, then there is no problem, and this load instruction can peacefully finishes its execution, and all the dependent instructions can take the value from this load instruction and execute their instructions. So, that means if there is no match, we do not have to flush anything here and we can proceed. And after some time, this load instruction can come to the head of the ROB, and then we can complete the execution of this load instruction, and at that particular point of time we update the architectural register. So, that means we update the corresponding register in the ARF by taking the value from the corresponding register in the RRF. So, we do that, and then with that we finish the out of order execution of an instruction. In order to execute this trailing load instructions ahead of the store instructions, and also minimize the penalty associated with the flushing this load instruction and subsequent dependent instructions, we have to use some data dependence prediction mechanisms to see whether our load instruction is independent of the previous store instructions, and whether we can execute the trailing load instructions speculatively ahead of the previous store instructions. And if our prediction mechanism is correct, then we can minimize the number of flushes, as well as we can improve the overall performance associated with the out of order execution of the instructions. So far we consider single ported data cache, where at any point of time only one load instruction can go to the data cache and read the data from the data cache. In order to improve the memory bandwidth, or in order to improve overlap the processing of multiple load instructions simultaneously by the data cache, what we can do is we can consider a dual ported the non-blocking cache. So, when we consider the dual ported data cache, so simultaneously we can service multiple load instructions by this data cache. Of course, when we consider dual ported, then we have to consider dual load units. In this particular design, we consider 2 read ports associated with the data cache. So, as a result, at any point of time 2 load instructions can read data from this data cache in their third pipeline stage of the load instruction processing. And also, in order to improve the overall bandwidth, we can consider this data cache as non-blocking cache, so that even if the previous instruction is not completed or finished its processing, this data cache can take new requests and then it starts processing. So, effectively at any point of time the data cache can service multiple requests coming from the processor. So, because of this dual ported non-blocking data cache, we can improve the overall the bandwidth and improve the overall performance of the system. So, with that we conclude the superscalar processor design. So, in summary, So, exploit instructional parallelism to improve the overall performance of the system. So, by using this compiler as well as the hardware techniques, we can expose the ILP that is there in our programs, so that we can improve the overall performance by executing these independent instructions on our underlying superscalar hardware units. And the key components in the dynamic scheduling associated with the superscalar processor are register renaming, reservation stations, reorder buffers, and operand forwarding. And we already discussed that register renaming eliminates name dependencies among instructions, and reservation stations will take care of Steckler hazards as well as the true dependencies. So, as a result, when we want to execute instructions in an out of order fashion, we have to respect the true dependencies, and as long as the true dependencies are respected, we can execute instruction in out of order fashion as long as the functional units are available, so that we can overlap the execution of multiple independent instructions by executing these instructions on different functional units available with our superscalar processor. And finally, in order to maintain the program correctness, we have to commit the instructions in order. So, to do that, we take the help of reorder buffer, which ensures in order commit of the instructions. And in order to improve the performance associated with the load and store instructions, we can exploit the load bypassing as well as the load forwarding mechanisms, so that we can execute load instructions in an out of order fashion and improve the overall performance. But in order to maintain the program correctness, we have to process our store instructions in the program order only. So, with that, I am concluding this superscalar processor unit design. Thank you.